I'm going to use this video to walk through the basics of Dcamp, a model that I built to predict diazotrophic cyanobacteria-associated metabolites, and I will outline the usefulness of this and how it can be used by the public as well. So let's start with the what of Dcamp. What is Dcamp? It's a model to predict the probability of a diazotrophic cyanobacteria in an environmental sample based on the secondary metabolites in that environmental sample. How does this model work? It uses secondary metabolites that are known to be associated either with diazotrophic or non-diazotrophic cyanobacteria, and it uses the similarity of their chemical fingerprints to other known cyanobacterial metabolites to determine the probability that that unknown chemical is diazotroph associated. And then we further went on to evaluate the performance of this approach using leave one out cross-validation. Now we'll get to the why behind Dcamp. One major research thrust in cyanobacteria is figuring out how they can fix nitrogen, especially since they are photosynthetic organisms and nitrogen fixation is supposed to be sensitive to oxygen that is produced by photosynthesis. So finding more of these diazotrophic cyanobacteria, also known as nitrogen-fixing cyanobacteria, creates more opportunity for scientists to discover new diazotrophic strategies. There are existing ways to identify diazotrophic cyanobacteria, such as the acetylene reduction assay, which requires a GCMS, or you can look for NIF gene sequences if there is sequencing available on the samples you're looking at. But if that's the case, they may not be novel samples and contribute to finding new strategies the same way that new environmental isolates would. Another advantage of this approach is that it may work when a strain is not actively fixing nitrogen, but is still producing the secondary metabolite that indicates it is capable of fixing nitrogen at some point. So the way this approach works is we have secondary metabolites from the Cyanomet database that are associated with known cyanobacterial strains. If we could find out that a given strain had a NIF gene reported in UniProt, a protein database, then we labeled it as a nitrogen-fixing organism. And if we could not find one and it had over 100 other proteins reported but no NIF gene reported, then we labeled it as non-diazotrophic for the purposes of this model. So let's say we have a novel secondary metabolite in an environmental sample and we want to use that to decide if there is likely diazotrophic cyanobacteria in that sample. What we would do is we would take the chemical fingerprint, compare it to all of our known metabolites that have a label. Whatever it matches most closely to, we are going to take its percent similarity and we're going to multiply that by 0.5. Now, if it is most similar to a diazotroph associated metabolite, we're going to add that 0.5 times its percent similarity to 0.5. So the highest number we could get here is 1. And then if it is most similar to a non-diazotroph associated metabolite, we're going to subtract 0.5 times its percent similarity. So the lowest number we could get is 0. When we're working percent similarity here, we convert, for example, 100% similarity to 1. So 98% similarity would be 0.98, and then you would multiply that by the 0.5 and go from there. The way we evaluated the performance of this approach was through a leave one out cross-validation, where we had all of our labeled samples, approximately 150, and we used all but one of them to train the model, and then we used that trained model to predict the one holdout, the one that was left out. And then we keep repeating that process, leaving a new one out of the training data every time until every single observation out of the approximately 150 labeled metabolites that we have was used as the holdout one time. From that, we were able to calculate the performance on the holdout, which showed an accuracy of almost 90% and pretty balanced performance, as we can see on the confusion matrix here, where a square in blue is showing that we predicted the true outcome, and a square in orange is that we incorrectly predicted the outcome. In addition to the accuracy metric, it also had a high area under the curve, and this is on the holdout data as well from the leave one out cross validation, indicating that its rank-wise performance is also very powerful, where a 1 would be a perfect score and 0.5 along this horizontal line would be only as good as random chance at ranking metabolites based on the probability they are diazotrophic cyanobacteria associated. So this would allow researchers to put in multiple metabolites and then rank them to prioritize which samples that they have are most worthy of their time of exploring first. Finally, we have the application itself, which is an R Shiny app, and the model is in the background of this. So on this first page, if you want to do an individual prediction, you can paste in the SMILES chemical code here, like so. And this is one that we actually used in our labeled data set. So we already knew this was a 0, meaning not diazotrophic. And we can see the prediction output is given here. It says based on atom pair similarity, so the chemical similarity to the labeled chemicals from Cyanomat database, the probability that this is diazotroph associated is 0. We see the visualization of the chemical here, and again, this was one from our data set that we knew for sure was non-diazotroph associated, and we can see it again right here. Now, if you want to do batch prediction, if you have multiple chemicals that you want to test, you can load them in like so, and in the background, it will do the predictions on all of the rows of your CSV. We'll see the format of that CSV here in a second. If you want to download the outputs, all you have to do is click this button. A link to the code repository and the supporting materials will be given in the description of this video.